Hi everybody, welcome back. This time we're going to talk about using Coulomb's law in vector notation, the real form of how Coulomb's law works, because after all, force is a vector and that needs to be taken into account in the equation. After that, we're going to get a brief introduction into electric fields and how to visualize electric fields. So first, Coulomb's law in correct vector notation says that the force, say, of between two charges is such that the force of charge 1 on charge 2 is equal to, well, kq1 q2 over r squared, where r is the distance between charge 1 and charge 2, literally the distance from charge 1 to charge 2, times a unit vector pointing from charge 1 to charge 2. Now, a lot of times we will state this as the force on charge 2 due to charge 1. In other words, F2, comma 1, force on charge 2 due to charge 1. And then it would be r hat of 2, comma 1. That's another common way of doing this. So just keep that in mind. That's how I will often write my notation. But both methods are methods that you will see in physics textbooks. So I should also mention that your textbook tends to use capital K instead of lowercase k for the Coulomb's constant, but I'll generally use the lowercase version because that tends to be more common. Now, you'll also sometimes see situations where textbooks only think of Coulomb's law as an equation for magnitude, and then they use geometry and like versus opposite charges to figure out directions in accordance with vector laws and everything. I think it's generally easier if you get used to using Coulomb's law in vector notation, especially when you're dealing with more than two charges. If there are just two charges around, fine, use Coulomb's law to find the magnitude in just magnitude form, and then use geometry to figure out direction. But I think a lot of times when you have more than two charges, especially if you have a continuous charge distribution, it tends to be easiest to just put everything in vector form and let the math work itself out. But really, you can just use whichever method is easier. So, without further ado, let's review the superposition principle. Remember, the superposition principle, back from kindergarten physics, tells you that whenever you're dealing with a vector field or any sort of vector force law or anything like that, the net force on some object is equal to the force due to, say, one object on it, plus the force due to another object on it, plus the force due to a third object on it, etc. And what that means is that the force acting on an object due to some random assortment of other objects around has nothing to do with the forces of those objects on each other. In other words, you just treat them as separate pairs, each object acting on the object of concern separately, and then add together all of the results. So for Coulomb's law, let's say you have a bunch of charges sprinkled around. Well, that would be, and you're wondering about the force on some charge Q due to that sprinkling of charge. Well, that would be kq1q over r1 squared times r1 hat plus kq2q over r2 squared times r2 hat, etc., where r1 hat and r2 hat respectively are the unit vectors pointing from charges 1 and 2 to charge q, and r1 and r2 are respectively the distances between charges q1 to q and q2 to q. Now, what is a unit vector? Remember, a unit vector is any vector that has a magnitude of 1. Well, what would r hat unit vector mean? Well, that would mean a vector that points in the direction of r1 vector, but only has a magnitude of 1. So how do we do that? Well, how about we just take the vector that is going directly from charge 1 to charge q in this example, and divide by the magnitude of that vector. What would r2 hat be? Well, it would be r2 vector, in other words, the vector going from charge 2 directly to charge q, divided by the magnitude of that vector, etc. Well, what does that mean? Well, r1 hat is going to be r1 vector divided by magnitude of r1. R2 hat is R2 vector divided by magnitude of R2. Well, that gives you an extra factor of the magnitude of that distance, that vector in there. Well, that's just the distance. So instead of having r's squared times unit vectors, we end up getting r's cubed times actual vectors. Either way is fine. I think what you're going to find is that in many situations, you're going to utilize writing it out as the full vector and dividing by the magnitude, and thus giving you an extra factor of r in the denominator of your Coulomb's law. In other situations, especially in situations with perpendicular symmetries and that sort of thing, you're going to just directly plug in the unit vector because you'll know the unit vector. For example, if your charges are all on, say, the x-axis, or all on the y-axis, or all on either the x-axis or the y-axis, in a lot of cases you'll know what those unit vectors are, especially if you're only concerned about the net force on the charge at the origin. So yeah, that superposition principle is incredibly important, so make sure that you're able to use it. We're going to be using it with forces, we're going to be using it with electric fields. Let's first get some intuition by taking a look at a one-dimensional problem. First, just in terms of magnitudes, and then using our common sense to figure out directions, and then in terms of vector force laws. So let's say you have a force on this charge Q right here due to Q1 and Q2. Well, that net force would be F1 vector plus F2 vector. Now, this free body diagram can only be right if the directions, in other words, the directions on this free body diagram can only be correct if, what is true? The blue charges must have opposite sign compared with the pink charge. Now, let's look at it at a calculation example. Calculate the force on each of the charges in this diagram. So first we'll look at the net force on the left charge, then we'll look at the net force on the middle charge, then we'll look at the net force on the rightmost charge. Well, what does that mean? Well, here again, we're just going to start off looking at it in terms of magnitudes and then using common sense to figure out directions. Well, just labeling the charges 1, 2, and 3 going from left to right, charges 1 and 2 exhibit a repulsive force on each other because they have the same sign. Charges 2 and 3 exhibit an attractive force because they have opposite signs, and charges 1 and 3 also exhibit attractive forces because they have opposite signs. So, what about the net force on charge 1? Well, we write down our givens and convert to SI units. In other words, get rid of the prefixes and just use scientific notation. And notice we also have our distances, R12, R21, are 4 micrometers, R23, R32, 3 micrometers, and don't forget the distance from charge 1 to charge 3, or from charge 3 to charge 1, 7 micrometers. Again, converted into scientific notation and SI units. So now the force on charge 1. Well, recognizing the charge 1 feels a repulsive force from charge 2, that's going to be toward the left, the negative direction. And then we just plug in absolute values for everything. And the force from charge 3 onto charge 1, well, that's an attractive force, which in this case is toward the right, the positive direction. So we smack a plus sign in front of that, the force on charge 1 due to charge 3. Yeah, a lot of times I just get rid of the commas in between those. Okay, well now we can factor out a common term, actually two common terms. K, absolute value Q1, factors out. That just makes it easier for us to plug in our givens. So we plug in our givens and we get that force. The fact that it's negative indicates that that force is to the left. The net force on charge 1 is to the left. And it's really big. That's a whole lot of newtons. Well, guess what? A millicoulomb is a whole lot of charge. And millicoulombs spaced apart by micrometers are really, really close together. That's going to be a huge amount of force. For the other two charges, we do the same thing. In this case, the middle charge feels a repulsive force from charge 1, making it go to the right. The middle charge feels an attractive force from charge 3, making it, again, go to the right. So in this case, we get plus signs both times. Factor out the common terms, plug in the numbers, and we get an even bigger force, again, toward the right. And then finally, for charge 3, that force is going to be to the left due to each of the other two charges. So we factor out common terms, and again plug in our numbers, giving us a net force on charge 3 of a big amount of newtons going toward the left. Now, ask yourself something. What would happen if we ended up adding up the net forces on each of these three charges? Just add them all up together. F1 net vector plus F2 net vector plus F3 net vector. Well, the result turns out to be 0. And hopefully that doesn't surprise you a whole lot, because that is in exact accordance with Newton's third law. There is no, and Newton's first law for that matter. All of the net forces must cancel, all of the force pairs must cancel out, and there is no net force acting on the system, which means that the net force must add up to be 0. So that's sometimes an important reality check to do on these types of problems. So if you realize that they don't add up to 0 in a problem like this, that means you've done something wrong. Boo! Now, what if we used unit vectors on that last problem? Well, we've already done it with all three charges. Let's just look at one of the charges in particular. Calculate the net force on charge 2. So that net force is going to be equal to the force on 2 due to charge 1 plus the force on 2 due to charge 3. And again, for each of those, we plug in Coulomb's law. And again, those unit vectors mean the unit vector, in this case, the unit vector pointing from charge 1 to charge 2. In other words, this is the unit vector toward charge 2 from where? From charge 1. This next one is the unit vector toward charge 2 from where? Charge 3. Okay. Now, we factor out a common term, but what are the unit vectors? Well, the unit vector from charge 1 to charge 2 is called I vector, or x hat is another name for it. The unit vector from charge 3 to charge 2 is negative I vector, or negative x hat. So, we plug those in. And now, the signs of the unit vectors and everything else with the unit vectors takes care of everything with the problem. And also the signs on the charges as well. And so in this case, the negative times the negative made the positive, and in this step we get exactly what we had at this point in the previous method of doing the problem. So in the end, we get 2.15 times 10 to the 16 newtons in the I direction. In other words, 2.15 times 10 to the 16 newtons in the positive x direction. What about for two-dimensional problems? So, in the case of two-dimensional problems, we could use superposition and think about attractive repulsive forces, but this is going to be a situation where, in my opinion, it's easiest to just use vectors the whole time. So, let's look at an example in 2 dimensions. Here we have 4 charged particles, each at the points of a rhombus, with charges given. Notice that the charges on each of the particles are different. So we have 4 different charged particles. Blue denotes negative charge, red denotes positive charge. In fact, that's a convention that you'll occasionally see. So let's calculate the force on charge Q3. So we write down our givens. Now notice our distances here. 2 of the distances are very easy. It's a rhombus, so each of the sides has a length of 6 centimeters. That is 0.06 meters. We're going to be plugging in our numbers in SI units. But what about the distance between charges 1 and 3? I think probably the easiest way to think about this is notice that this is, I guess you could call it an equilateral rhombus, even though obviously a truly equilateral rhombus would be called a square. But you have, if you were to make a dividing line between the 2 positive charges, that would show you that you have this rhombus being composed of 2 equilateral triangles, just kind of stitched together. And what that means is that the distance from charge 2 to 4 is 6 centimeters, which means that half the distance between charge 2 and 4 is 3 centimeters. In other words, the distance from either charge 2 or 4 to the midpoint of the rhombus is 3 centimeters. Well, that's a 30, 60, 90 right triangle. So we know about 30, 60, 90 right triangles. If the distance from along the small base is 3 centimeters, then that means the distance along the bigger base, so to speak, is 3 centimeters times the square root of 3. Well, Just double that to get the distance from Q1 to Q3, and you have 6 centimeters times the square root of 3. So, how do we figure out the force on charge 3? Well, that's by the superposition principle. That's the force on charge 3 due to charge 1, plus the force on charge 3 due to charge 2, plus the force on charge 3 due to charge 4. Again, that's going to happen anytime you have a vector field force law, in which the electric field is a vector field. We'll have more to say about that soon. Anyway, that means 3 Coulomb's law expressions that are going to be added up, where each Coulomb's law magnitude is multiplied by the unit vector going from that particular charge to the charge that we care about. In other words, R3, 1 is the unit vector pointing toward charge 3 from where? Charge 1. And we do the same thing for all of the others. So we have K, Q3, Q2 over R3, 2 squared. That is the distance to charge 3 from charge 2 times R hat from charge 2 to charge 3, or the unit vector pointing at charge 3 from charge 2 plus etc. from charge 4. Now, we can again factor out a common term, the KQ, and the main problem that we're going to be dealing with is figuring out what these vectors actually are. So there's a little trick to dealing with these vectors. Any time you have a unit vector can be alternatively written as just a vector, an ordinary vector going from one point to the point of concern, divided by the magnitude of the vector. In other words, divided by the distance in this case. Now, that's true in general. In other words, it doesn't have to be in distance space. It can be in any sort of vector space. All you have is just the unit vector from one point in that space to another point in that space is equal to the actual vector between those 2 points divided by the magnitude of that vector. And boom, you've got a unit vector. Okay, so that's what we're going to use in figuring out the rest of this problem. So, first of all, we have a KQ3. We're going to factor that out, and then we can actually just plug in our K and our Q3. But that's going to be multiplied by a whole bunch of stuff. Now notice that in this case, after I factored out my KQ3, I rewrote each of my unit vectors as the vector, the actual vector, in this case, the unit vector from charge 1 to charge 3 is equal to the actual vector from charge 1 to charge 3 divided by the magnitude of that vector. Well, that's nice. We already have the magnitude of that vector. Now all we need is the actual vector itself. In fact, this is an approximate form of the magnitude, 0.1039 meters, which I got by taking 6 times the square root of 3 and just rounding it out to 4 sig figs. And similarly, the unit vector going from charge 2 to charge 3, that's going to be easy to write, but it's still the actual vector going from charge 2 to charge 3 divided by its magnitude, and the unit vector going from charge 4 to charge 3 is the actual vector from 4 to 3 divided by that vector's magnitude. Of course, each of those magnitudes we know is just 6 centimeters, or 0.06 meters. Now, what is all of this stuff? How are we going to get the hard unit vectors, so to speak, or at least the hard vectors? It helps to imagine this rhombus on a coordinate plane and pretend that charge 1 is at the point 0, 0. Well, if charge 1 is at the point 0, 0, then, well, I can go over 6 centimeters to get to charge 4, and then go over another 3 centimeters to get right smack below charge 3. So apparently the x component of my vector going from charge 1 to charge 3, that is R3, 1 vector, is just 9 centimeters. That's the x component. What about the y component? Well, again, this is kind of the base of that 30, 60, 90 right triangle. We know that the hypotenuse here is 6 centimeters, so the base is 3 centimeters, and that also means that the height would end up being 3 times the square root of 3 centimeters. So that's how we get that. So apparently the vector going from charge 1 to charge 3 is going to be 9 centimeters I vector plus 3 square roots of 3 centimeters J vector. And I factored out the centimeters there. The unit vector going from charge 2 to charge 3 is very easy, just 6 centimeters I. And the unit vector going from charge 4 to charge 3, well, 3 centimeters in the x direction And then, as we mentioned already, 3 squared roots of 3 centimeters in the y direction. So 3I plus 3 squared roots of 3j centimeters. Okay, so now we have our vectors, we know the magnitudes, and I know you all must be running for the hills now because, uh-oh, I'm using smaller font. Yeah, so we have a lot to plug in here. And basically, here's the stuff. Now, I factored out centimeters here because I saw that I was going to be having centimeters for each of my unit vectors here. Or sorry, each of my vectors, it's some number of centimeters. So I factored out that 0.01 meters here and just brought it out front. And then I plugged in everything else. So there's my R31 vector, there's my R32 vector, there's my R34 vector. And notice that in the denominator, we have the magnitude cubed. That doesn't change the fact that Coulomb's law is a 1 over r squared force law. We just get the r cubed because of the fact that we decided to write out our unit vector as vector divided by magnitude, giving us another factor of magnitude, which we collapsed into the denominator. Okay, so now how do you add up vectors? Well, you combine like terms. The same way that you would add up polynomials. You combine like terms. So, what do? We group all of our I terms together, all of our x components together, and we group all of our j terms, all of our y components together. I also did a little bit of math here. Out in front, I combined my Coulomb constant with my Q3 and my 0.01 meters. And I also noted that I have coulombs that will factor out of this expression for units, giving me a Coulomb squared out here when you combine with this other coulombs here. Oh, that cancels the Coulomb square in the denominator. That's nice. And we have a meters squared times meters out here. That's a meters cubed. Well, we can also factor out a 1 over meters cubed in our units out here. So that's why the only thing that's left over is newtons. And I didn't plug in any units here because it would be wrong to plug them in. I already factored them out and canceled them. So, yes, I am showing units here, but I have simplified. Sneaky, sneaky, sneaky. So, now we're just ready to plug everything into the calculator. And after we do that, we get that our net force vector acting on charge 3 is negative 3.63I minus 0.80J times 10 to the minus 3 newtons. Now, do the relative components, do the relative magnitudes of our components and their directions make sense? Well, let's look back at this. So we have a charge Q4 down here. That's going to be tugging this a little bit downward. And we also have a charge Q1 over here. It's farther away, so that's going to be kind of pushing Q3 a little bit upward, but the closer proximity of Q4 and its downward tug is going to give us a net downward tug here. But there's a little bit of a cancellation, so that's going to have a smaller magnitude than our x component. What about our x component? Well, our x component is dealing with a slight push toward the upper right from Q1, which is far away, but a big pull to the left from Q2, which is nearby, and another pull in a leftward direction due to Q4, which is also closer. So it does make sense that our x component has a noticeably larger magnitude than our y component here. So that's a good reality check on these types of problems. Now, what about this electric field that I keep mentioning? Whenever you have a charged particle, you can imagine that there's this invisible field that emanates from that charged particle. What does this field do? It tells other charged particles what force they must feel. If there are any other charged particles around, it tells them what force they are, what force they would experience. Now, in addition to that, it actually truly does permeate into space. In other words, it gives the space around the charge some energy. So that's something that we're going to come back to when we get into chapter 34 near the end of the course. The idea for the electric field goes to Michael Faraday, though in truth fields were used as a concept a good bit before. For example, Pierre-Simon de Laplace came up with the idea with gravitational fields a while back before Michael Faraday, but still Michael Faraday gets credit for the electric field. A lot of times you will have problems that discuss the electric field strength. That's code for take the magnitude of the electric field. In other words, electric field is a vector. It has a magnitude, called the electric field strength, and a direction, called the direction. So the idea is that whenever an electric charge is present, there's a field everywhere in space, and it influences other charges by exerting forces on them. And that field, not surprisingly, exhibits a 1 over distance squared force law, just like gravity, just like Coulomb's law. Oh, there's a good reason for that. Because the electric field is defined as the force vector per unit charge. In other words, you tell me how much charge is there, and if you know the electric field, or if I know the electric field, I'll tell you how much force that charge is going to feel. So you might wonder, it's like, well, why not just work from Coulomb's law and calculate the force? The answer is, first of all, it's often easier just to calculate the electric field. Easier to calculate the electric field than it would be just to directly calculate the force. And we're going to be dealing with this a lot once we get into integration in the next chapter. And in chapter 27, we're actually going to develop a very powerful tool, Gauss's law, that allows us to quickly determine electric fields for three-dimensional charge distributions. And another thing is, once you've determined the electric field, that is the electric field. If anybody wants to know the force, just ask them, how much charge are you putting there? And if they change their mind and decide to put a different amount of charge there, you don't have to start your calculation from scratch again. You just go back to the electric field that you've already calculated and multiply by their new charge. So, for point charges, the electric field strength, well, Coulomb's law for a point charge, kq1 q2 over r squared. Well, let's pretend that it's kq q1 over r squared, and the force per unit charge, if our test charge is q1, well, force per q1, just divide out the q1, you're left with just kq over r squared. That's the electric field strength of a point charge. Now again, electric force is a vector, so electric field is a vector. So the superposition principle applies here as well, which is very good because this will allow us to use calculus in the rest of this unit when we are dealing with continuous charge distributions. Now, the electric field vector due to a spherically symmetric charge distribution is given by, well, the kind of Coulomb expression, kq over r squared, times the unit vector going outward from the center of your charge distribution. Now, you might notice that there's something funny about this r here. Was this a typo? No, this was not a typo. Because here's the thing. When you get into more advanced electromagnetism stuff, for example, if you end up being a physics or engineering major in college and you end up taking electromagnetism probably around your 3rd or 4th year in college, you're going to encounter situations where you'll have a spherical charge distribution of radius big R located at a position vector of radius little r from the origin. And you might have other charges around and stuff like that. So curly r simply denotes the distance from your spherical charge distribution, from the center of that, if it's in an arbitrary location, like for example if it's not at the origin. And curly r hat would be the unit vector going outward from your spherical charge distribution. Now, in AP Physics and freshman undergrad university physics, we pretend to be civilized people, and the vast majority of the time, this curly r is just going to be lowercase r. So I wanted to put it like that just for you all to keep in mind. But in a whole lot of the problems that I'm going to do, I'm just going to call it kq over little r squared without any fancy cursive or anything like that. So I've already mentioned before that sometimes the Coulomb constant lowercase k is replaced by capital K. And there's another thing to keep in mind. A lot of times it's replaced by 1 over 4 pi epsilon naught. In fact, that happens much more often than you would see lowercase k replaced by capital K. The reason is because in a lot of situations, the amount of charge that you have, like in your kq over r squared expression, the amount of charge you have has something to do with some sort of volume charge distribution. And when you work that out, you end up getting a 4 pi that likes to cancel with that 1 over 4, with that 4 pi and the 1 over 4 pi epsilon naught representation of the Coulomb constant K. So that's something to keep in mind. Should you use K, or should you use 1 over 4 pi epsilon naught for 8.98755, etc., times 10 to the 9 Newton meters squared per Coulomb squared? Which one should you use? It just depends. If you expect that you're going to get a factor of 4 pi in one of your charges, then you might as well just call it 1 over 4 pi epsilon naught. If you're not expecting such a factor, call it K and use kq over r squared, or K or whatever comes after that, depending on your charge distribution. So it's your choice. Now, how do we draw electric fields? There are computer programs that can really aid in visualizing electric fields. The PhET simulations from University of Colorado have a couple of nice electric field simulators, so that's something to keep in mind. But let's say you're told to draw it by hand. So the internet's down, the power's out, or whatever. So you have to draw electric fields by hand. So the idea is that you want to make sure that the electric field represents the initial path that a very small test charge would take. And I say path here. What I really mean is the initial path. And a test charge means a very small positive charge that is so small in magnitude that it doesn't actually affect the electric field. And again, it's a positive test charge, so that's the idea is that it's going to go in the direction of your electric field lines, because the electric field lines are defined such that they would give you the direction of the initial force, well, actually just the direction of the force on a small positive test charge. So in this case, where we have a smattering of negative charge in a relatively spherical distribution here, if you imagine a small positive charge, well, that's going to, no matter where you put it around this negative charge distribution, it's going to feel a force toward the center of that negative charge distribution. So when we go down here and actually draw our field, we're going to have a bunch of field lines pointing inward toward the center of our negative charge distribution. So how do you draw a field line? Well, you pick a point and you imagine putting a very small positive charge there and figure out what the force on that point would be from all of the other charges in the universe. Not just the one nearby, but all of the other ones out there. Don't forget about all of those charges in the Alpha Centauri system and stuff like that. So then you draw an arrow in the direction of the force. The bigger the force, the bigger the arrow. And keep in mind some rules. Field lines always start on a positive charge and end on a negative charge. If you don't have a negative charge in your picture, then field lines just kind of go out into space and you pretend that they will eventually find negative charges on which to end. And the number of field lines flowing from a positive charge or into a negative charge should be proportional to the magnitude of the charge. For example, if you have several charges around, one has a magnitude of 1 and the other has a magnitude of 2, the charge with a magnitude of 2 should have twice as many field lines going into it or out of it as the charge with the magnitude of 1 has. And you will use arrows to show the direction that a positive charge would initially move if it was released from rest. Again, we're talking about initial directions, in other words, the direction of the force. So, electric field lines show the initial path that a small test charge would take. I really should edit this. So, the initial path. Field lines never cross. Think, what would happen if they did? Well, if they did, that would mean that the electric field is undefined at that location. And if it's undefined at that location, that would mean that something called the electric potential does not exist. And we're going to talk a lot more about the electric potential in a future unit and why an undefined electric field would mean that the electric potential wouldn't exist It has to do with the fact that the electric field is a conservative field. It's a conservative vector field. And again, number of field lines is proportional to the size of the charge. What does that mean? It means that the number of field lines per unit area is proportional to the strength of the electric field. And again, you begin at a positive and end at a negative. So, you have positive charge here, lots of field lines going out of it, and many of them end on this negative charge down here. We do show some field lines coming out from the positive that just don't seem to end anywhere, but presumably outside of the bounds of this picture, they end up curling around and eventually coming into this negative charge, using field lines also coming from outside the bounds of this picture. This is, of course, assuming that there are only two charges in the universe. But guess what? In this class, you are always supposed to assume that the only charges around are the ones that you're told about. And here we have this nice centipede diagram. So I call it that simply because it does look a lot like those little house critters that you see skittering across your basement walls at 50 miles an hour. So in this case, if you were to just imagine putting a small, tiny positive test charge near one of these charges, it would initially feel a force going away from it. In other words, the electric field is going outward like this. The electric field vector at any point in an electric field distribution is always going to be tangent to the path of the electric field lines. Now, that does not mean, as I've tried to emphasize before, that does not mean that if you were to release a charge here, that it would just travel along a field line. The charge would actually not travel along a field line, in spite of the statements that I might have misled you with in some of the previous slides. It would feel a force anywhere along the field line. It would feel a force in that direction. But if it's already moving, then, well, there's that velocity component on there, and that velocity, its momentum, is going to end up taking it into different field lines. So if I was to release this charge right here, then it might end up actually taking a path of something like this. Whoop, it suddenly got accelerated over here. Now it has velocity. That kind of takes it in this direction, and it kind of might end up veering off over here. So that's something very important to keep in mind. How about a cockroach diagram? So here we have a charge of +1 and a charge of -2. This was a drawing that I just did for a class like 10 years ago, where I decided I wanted to have four field lines coming out of my +1 charge. Well, that means I need to have 8 field lines going into the -2 charge. And in this diagram, all 4 of the ones coming out of the +1 end up going into the -2 charge. And since it's a -2 charge, that means it also needs to have 4 others coming into it from presumably some other positive charges somewhere else in the universe. Now, what about a praying mantis diagram? Here we have a charge of +3 and 2 other charges, a -2 and a -1. So in this case, the charges actually balance out. So the number of field lines coming into the picture must be the same as the number of field lines going out of the picture. Ooh, that's actually related to something really, really deep that we're going to end up getting to in chapter 27. It's basically related to Gauss's law. But in any case, since I have 4 field lines going into my -1 charge, that means I need to have 8 going into the -2 and 12 coming out of the +3. Because after all, 12 is 4 times 3. So those are kind of some examples of how you would draw electric fields. Now, what about this electrostatic equilibrium concept that we've already mentioned in a previous video? So electrostatic equilibrium means that there is no net motion of charge. Things are relaxed. And that happens extremely quickly in the case of conductors, like very, very fast. Whenever you try to exert an electric field outside of a conductor, the charges very quickly move around until they are in electrostatic equilibrium. A result of this is that the electric field is 0 everywhere inside of a conductor, unless you happen to have some extra charge that you have snuck into the middle of the conductor. So what would happen if this was not true? In that case, well, charge would move, because electric field tells you the force per unit charge on the charge, and that would contradict the statement of electrostatic equilibrium. And we just said that we have electrostatic equilibrium. The charges aren't moving. A Faraday cage is an all-encompassing conductive barrier, and it does not need to be elaborate. A lot of times just chicken wire around yourself will work as a perfect Faraday cage, so that if the chicken wire gets struck by lightning, you will not be electrocuted. You might be baked because of the heat of the lightning, but hey, at least you won't be electrocuted. Metal frames of automobiles, as we mentioned before, provide safety from lightning. And of course it's not the insulation of the rubber tires. So anyway, since there's no net motion of charge, that means that any excess charge on a conductor must be at the surface, unless somebody happens to sneak some charge inside of the conductor and holds it there somehow with some sort of other barrier, or at least some props or something like that. That's a problem that occasionally comes up on the AP exam. So there's no net motion of charge. Any excess charge is on the surface. Now, it turns out that this would not necessarily be true if there was something other than a 1 over r squared dependence on individual charges. And a nice proof of that comes from Gauss's law, which we will discuss in a couple of chapters. Now, another thing is that the electric field on the surface of a conductor is always perpendicular to the surface. It's not necessarily true for an insulator, but it's always true for a conductor. In fact, if that wasn't true, that would mean that there would be a sideways component of the electric field vector. In other words, a component of the field vector that is parallel to the surface, and that would mean that there would be a force that is parallel to the surface and the charges would move around. Whoops, I thought we were in electrostatic equilibrium. Oh, apparently not if the charges are moving around. So, electrostatic equilibrium, once that's attained, the electric field is perpendicular everywhere to the surface. And charges also, let's say you have some kind of funny shaped conductor like a triangle, that would mean that the charges tend to accumulate preferentially at the pointy ends. The exact reason for this has to do with the fact that the electric potential, which we're going to discuss in a future unit, is the same everywhere on the surface of a conductor. The electric field is not, but the electric potential always is. Conductors are what we call equipotential surfaces. And that's why whenever you connect a wire between two charge sources, everything ends up being equal and the voltage on both charge areas ends up being equal, because the whole thing becomes a conductor. Equipotential means same voltage. Now, I should mention, just to address a common misconception that you might have come across if you've been hanging out on some of the not so nice street corners of a bad area or something like that, you might have heard people whispering that the sharp points on lightning rods allow the charge that accumulates on a house during a thunderstorm to dissipate out into the air so that the house doesn't get struck by lightning, and the lightning rod prevents any lightning strike from happening nearby. That is not true. The sharp points on the lightning rods, they do help a little bit to ionize the surrounding air around that point, but what that does in the case of a thunderstorm is it actually attracts lightning there. It attracts lightning there. And as such, when the lightning gets attracted there, it goes into the rod. The rod's an equipotential surface, and the rod is in contact with the ground. It better be in contact with the ground, otherwise your house is going to get blown to smithereens. Maybe. But in any case, yeah, the leaking of charge off the pointy ends of our lightning rod during a typical thunderstorm is not fast enough to drain the charge from the house. So, in any case, the lightning rod is to attract the lightning there so that the strike does happen on the rod and then gets redirected into the ground. In fact, in a lot of areas like it, I've heard that it happens in Europe. I've seen it in China. The lightning rods will actually be spherical balls at the end of metal poles. So, summary of conductors and electrostatic equilibrium. The electric field is zero at all points inside the conducting medium. That is, any part that's metal, the electric field there is zero. And the electric field is zero inside any conducting shell that is, say, like, let's say you have a hollow conductor. Inside of that conducting shell, inside the hollow area where you might have, say, a person trying to get shielded from getting zapped, you're going to have zero electric field unless that person has brought in extra charge. And if there's extra charge, then the electric field would just be calculated based only on that extra charge. The only charge that is going to be actually, the only net charge that's going to be on the metal itself is going to be at the surface. and the electric field is always normal, that is perpendicular to the surface. And charge also tends to get concentrated into areas with the smallest radius of curvature. So let's say you have say a capacitor here, and you put a conducting ball into the middle of that capacitor. Well, if the left side is positively charged, the right side is negatively charged, that would mean that if you didn't have this conducting ball here, the electric field lines would just go directly from left to right. We'll explore this in more detail in chapter 26. But by bringing this conducting ball in there, remember that electric field lines must always be perpendicular to a conducting surface, so continuing to go sideways and right here would not work. That would not be perpendicular to the surface unless you're hitting right at the midpoint of the conducting ball. That means that the field ends up getting distorted when you bring a conductor in between an area of what had otherwise been constant electric field. And if you hollowed out a cavity in there, the electric field would be zero inside of that cavity unless somebody pinned some sort of charge into the middle of that cavity. And I say pinned because if you didn't pin it there, it would eventually drift off and meet a surface, and then it would stay on the surface. So this has hopefully been an effective summary of an introduction to electric forces, how to use Coulomb's law in one dimension, how to use the vector form of Coulomb's law in both 1 and 2 dimensions, and then an early introduction into electric fields. We will have a lot more to say about electric fields, including how to calculate electric fields of continuous charge distributions, how to approximate electric fields due to dipoles and quadrupoles, and other applications starting in our next video when we get into an entire chapter having to do with electric fields. So until then, thank you all for watching, and if you have any questions or comments, leave them in the YouTube comments.